We'll basically continue talking about multiplicative weight update. Okay, and you will see what I mean by width reduction. Okay, so let me recap what happened last time. So we have that we start with like some non-negative matrix that describe the LP. And once you can write the LP based on the matrix A like this. So this is a packing LP, and then this would be a covering LP. Like the difference is just packing LP will try to maximize, and the constraint is at most. Covering LP try to minimize things, and bullshit. And the constraint is to say that it's at least constraint. Okay, right. And this is just a standard form of the packing and covering LP. In general, you see that this doesn't need to be 1. This also doesn't need to be 1. Okay, so and the input that we have is basically packing, covering LP, and we have the parameter epsilon and opt, and we basically want to know whether whether there is a solution that is at least opt or not, up to some approximation factor that depends on epsilon. Okay, and how do we do this? Well, we look at the oracle problem, right? And the oracle problem is basically kind of relaxation of the packing LP, okay. Where we just ask can we find X such that the objective is at least opt, and the inequality, the constraint here is basically collapsed to 1 by multiplying with the weights on every constraint and then sum them up. And okay, and the algorithm was basically to keep calling the oracle, initialize the weight to be the weight. So for each constraint to be 1, repeat several times, call the oracle with respect to the current weight. If it returns infeasible, then you know that you can return some dual solution. Otherwise, it returns the oracle returns some not feasible primal solution. It's not feasible because it's just feasible for the oracle, not feasible for the original LP. It returns some xt. This xt define the gain vector. Then from this gain vector you update the weights for each constraint of the primal LP. Repeat this several times. At the end you just return compute the average of all the x here and scale it down by a bit, and you return x. And what we have seen last time is that if it returns y, this is going to be just a feasible dual solution and with value opt. If it returns x, this will also be a feasible primal solution with value some basically opt, at least opt over some 1 plus epsilon. Okay, so I will not prove this, we have seen this. Okay. The running time of this algorithm basically is dictated by the oracle, because it really just keep calling the oracle several times. And if the oracle has width row, by row here I mean this thing, when you multiply x to a, the axt is at most row times 1. So basically each constraint is violated by at most row factor. Okay. So if the oracle has width row, then the algorithm will just need to repeat basically row many iteration And in each iteration, we just call Oracle once, and then we just need to update the weights. So which weight do we update? Just the weight that basically involve the that involve the Oracle output, like that involve xt. Yeah. So we update the weights on ht, and ht is defined by xt. Okay, so that's basically if you have an efficient oracle with low width, then the whole algorithm is going to be fast. And we see at least one way to implement an oracle, right? Kind of compute the best bang per buck variable. That is, you basically look into so recorded the oracle want to find x such that this is true and a at most. Okay. So it's just like some non-negative, like a two constraint with non-negative coefficient. And the way to solve this is just to find the best bang per buck variable x. What do I mean? It's just the variable x e prime with smallest coefficient in this one. Once you find it, then and in other words, it's just e prime such that when you multiply w to a here, the coordinate e is the minimum one. So that's e prime. Just need to compute this. Once you find e prime, then you just set x e prime to be opt, and the rest is 0. So once you set x e prime to be opt, this is going to be certified, and then you can check if this is certified or not. If this is certified by setting x e prime to be opt, then we are good. Two constraints are certified. If it's not, then we know that there is no way to certify this anyway, because even when you put the best bang per buck one to certify the first one, the second constraint still is not certified, so you can conclude that it's infeasible. So that's the whole algorithm.
I don't know if we've gone over this, but do you have to worry about the runtime to compute A transpose W or W transpose A?
Very good question. So basically you see that the whole running time here is just depends on computing A times W. And now it depends on the problem, how fast we can compute this. Okay, and last time we see that for matching, when the problem is to compute matching, like the maximum matching, it's fast at that time, because for matching, right? What do we have? We have that AX here is just for every node V, E contains V. This is this thing. This is AX, and when you multiply by W, this is just sum over all nodes, right? And this is just nothing. This is just the same thing. If I rearrange, you can write it like this. XE when E is UV. So to compute the X with smallest coefficient in this expression, when your goal is to compute matching, it just simplify to finding the HE such that this thing is minimized. the sum of its endpoint is minimized. That's what we did last time. You remember? Okay. So finding an edge such that the sum of its endpoint, sum of the weight on the endpoint is minimized, can do it in linear time. Just really scan through all edges. For each edge, just sum its endpoint. Okay. So for matching, it's linear time. And we're gonna see today, like, what if it's different problem? Like how fast you can do this for different problem like MacFlow. So question up to now, this is just to recap. Okay, so let's try to, let's try to apply this framework to solve MacFlow, right? Let's say you have a graph with n vertices and m edges, right? And let's say each edge has unit capacity. Capacity is just 1. And we know that we can capture this problem by an LP. Maximum ST flow can be written in this way. This is the LP that captures maximum flow. That is, XP is the flow along the path P. For each path P from S to T, you have the variable XP, right? And here just to say that the total flow along every path that goes through an HE is at most 1. So it respects the capacity, and here you want to maximize the flow value. Yeah.
So this is only the unit version.
Unit version.
Okay.
Yeah.
Oh wait, yeah, it's the same.
Right. Okay. So if we want to solve this problem with a multiplicative weight update framework, questions? Okay. Then the only thing we need to ask yourself is just, okay, how do you implement the oracle? That's all, right? And one way is just to implement the best bang per buck oracle. So let's try to ask, what is if you look at this, how you have this LP, what would be the best bang per buck variable when you try to solve the oracle problem? Yeah.
So I think it would be the path with the fewest edges, which would be the shortest path, right?
The path with the fewest edges, that's close, but not yet, not quite correct yet. So let's try to do it together. So the point is that, let's try to look at what is the best bang per buck variable. Note that for each round in the weight update algorithm, the whole framework will maintain some weights, right? There is going to be a weight for each constraint, for each packing constraint. So you have weight WE for each HE. And what we need to do is just to multiply WE to each of the, you have the weight WE, multiply to this thing, and then sum them up over all edges. So this is what we're going to do. Just look at this part. Multiply WE to the left-hand side of the constraint, and sum them up. And now you want to see what you want to see is what is the smallest, what is the XP with smallest coefficient. So to do this, we need to rearrange the sum, and then you get this. Right? I just rearranged the sum. Now it's summing over all paths instead, and you get XP. what's the coefficient of xp? It's really just like all edges in the path and like summing over all the weight of E. Okay, now it should be clear. What is the path with smallest coefficient? So it's not quite a path with smallest number of edges, but what? Yeah.
It's smallest number of, or it's shortest path when you use the weights as like distance.
Exactly.
For each edge.
Yeah, it's really just the shortest path from S to T when the weight on each edge is W. And so that's all we need to find the best bang per buck variable. It's just to find the shortest path from S to T when the weight is W. How fast can we do this?
An exponential time. If we're going over every. Oh wait, no. If you go over like, just do like Dijkstra's or something, you can do it linearly.
Yeah, there are exponentially many paths, true, but we just want the smallest path. And that is just Dijkstra algorithm. Like you can use it using Dijkstra, Bellman-Ford, anything. So you see, like even though this LP is exponentially large, when you look at the oracle problem, like it's just polynomial time problem. That can happen, and like it's just gonna be useful many times. That's why like this framework is quite nice. So the best bang per buck variable xp is just the path p prime xp prime, such that like this basically the weight of this path is minimized, which is just the st shortest path when the weight is w. So the algorithm is just gonna set value up to this path, and the rest is 0. And now we just need to analyze this oracle, where the running time is m plus n log n. That's the running time of Dijkstra when you use Fibonacci heap. Right? And let's look at the width. How bad is this, right? So we just need to look at how bad when you return this x, how badly does it violate each constraint. So just need to look at each constraint. Like look at this constraint. How badly this is much more than 1. Okay, so just need to analyze. Well, you'll have this as like you want to bound this one, but this is gonna be at most x p prime, because we really just set one path p prime to be value of opt. Nothing else is non-zero. So this is at most x p prime is at most opt. So this is the width basically is at most opt. Now we can ask like how big opt can be. Well, when it's max flow with unit capacity, you know that each edge can each edge can have only one unit of flow going through it. So the maximum flow is at most number of edges. So in this case, well, in the unit capacity case, opt is at most m. So you see that the width is at most m. It's not that great, it's not too small, but it's something that is polynomial. Okay. So now, so let's interpret this. So we are done with the oracle, right? So now let's look at what happened when we plug in this oracle. Let's interpret what is this algorithm. It really just you start with some weight function, and we just compute the shortest path p prime, and like the oracle will return this shortest path, and then we're gonna update the weights, and the weight of which constraint will be updated is just gonna be the weight on every edge of P prime. So you see, like okay, maybe I see. So you see that like we just update this one, like update the weight for every constraint according to h. And like I claim that so okay. So basically, we really just ask like for every edge, like look at each constraint. So basically, what we do here is like we update the weight, of constraint E proportion to what? Proportion to like according to how big this thing is. At the variable, like at the constraint of E, right? And like when you return P prime, well, like the constraint that doesn't contain the path P prime at all, this will be 0, right? So only when E is in P prime, then this is non-zero. So you see that the algorithm just gonna update the weight along along edges of the path. So you can see that how the algorithm looks like. It's like this. Like you start with S and T. Initially, the weight of every edge is 1, right? And the algorithm just compute in the first round. Really, just compute shortest path with smallest number of edges, and it compute the path. And then it's just gonna increase the weight along this one, along the path. And then next it's gonna compute another path. And like you see that the algorithm kind of have some incentive not to repeat the same path because you want shortest path, right? So you just keep computing shortest path again and again, and you should intuitively see that like it's gonna basically try to use like different paths again and again, and that's why like intuitively the flow will kind of spread, like the path that you find in each iteration will try to spread out, and that's why it makes sense that this will compute max flow at the end when you average all the paths together.
So my intuition, this might only be like correct with the integral version, but like if we find a shortest path, then like we can add that path to our solution, but then shouldn't we like never take that path again if each capacity is 1? Or is the reason that we can't do that is because it's like this is a fractional problem?
So good. So note this. We actually gonna compute like many paths. So you should think like, so the number of iteration is gonna be something like rho log n which is something like m in this case. And you should think like for each of the paths here, and like remember that what we do is like we return this path, right? And then we sum them up and then we average them. So all these paths actually like have really small flow value because we average over m many paths.
Okay.
Yeah. So like the flow value on each of these paths is going to be something like op over m. Because each path we put op value and we at the end we average over m path. So that's why like it's okay to reuse some of things on this path. Yeah. Okay. And yeah, it's a really intuitive algorithm. Just find shortest path, repeat, and at the end and you incentivize the algorithm to not repeating by increasing the weights. And yeah, so that will give like this is like a simple heuristic, but it works from weight update framework. And you see that this is kind of simpler than in some sense simpler than the previous max flow algorithm that you have seen, that you need to talk about residual graph, you need to cancel the flow. Nothing like that. Yeah. Okay. And the algorithm will take this time. This is the number of iteration because this is the width, right? And in each round, you need to find a shortest path. And in each round, you need to update the weights. The number of edges that you need to update is just going to be along the path. So that's at most n. There are n edges along the path. So that gives you something like m squared over epsilon with O tilde here high some polylog factor.
Is there an easy way to extend this to max flow with like not unit capacities?
Yes. So we're gonna do it now.
Oh, okay.
Yeah. So this is like next is like some example with the problem with weight and capacity.
Okay.
Okay. So let's do it for matching first, right? Okay. So for matching, well, you start with this LP. This is the maximum, let's say maximum cost matching. Let's call cost because I need to use something that is not W. Okay. So we want to maximize the cost of the matching, and the cost of each edge is CE. Okay. So we can turn it into the standard form like this. Okay. And now, okay, the only thing you need to ask is, what is the best bang per buck variable when you implement an oracle? So you are given the weights for each constraint. So now it's going to be the weight for each node. We have the weight for each constraint. So just, yeah. So you have the weight for each constraint. Just sum them up for overall, like the weight for each constraint multiplied to the constraint here, which is this one CE times XE. Multiply this to the weight to the constraint and that sum them up. Well, now this gives you something. It's gonna give you, just rearrange. This is just gonna be W when E is UV, and you're gonna have CE here. So find XE such that this coefficient is minimized. So that's all. Yeah. Just need to find this one, and this you can do it in linear time clearly. That's it. But okay, you can find the best bang per buck variable easily, just here. But now you need to compute the width as well. But like we will see that the width is not as good. It's not just gonna be like n. It's gonna depends on the max and min cost of edges. So let's see. Let's just see a bit why, right? Because what you're gonna do is you're just gonna put like basically we just say that okay, we put this thing and we ask how big this can be when our algorithm return given the Oracle solution, how big this can be. And this is just gonna be at most when we're gonna have basically at most x e prime over c e prime. When e prime is the best bang per buck variable, and x e prime is opt over e prime, right? So in general, this thing can be as bad as opt over min e c e. So this is gonna be our width. Okay. And how big opt can be? There can be n edges in the meshing. Each edge can have cost as big as max CE. So this is the width at most. We can bound the width in this way. So when the cost is uniform, it's unweighted, like unit cost, this is just n. But you can see that when the cost can be like a very different between edges, this is not that great. So this technique basically will give you like a simple way to implement the Oracle, but the width is going to be quite bad when you have weights or capacity. Okay. So this is not really polynomial because it depends on this thing. Let's try to look at what happens when you have capacitated graph for max flow. Okay. So here for max flow with capacity, let's say U is a capacity for H. UE is the capacity for HE. Previous problem you have something that is not 1 here. This problem you have something that is not 1 here. Okay. But okay, if you want to solve this problem, just turn it to the standard form like this and see what happens. Like ask the same question: what's the best bang per buck variable? Right. Just repeat like before. You're gonna see that like the best bang per buck variable is just a path p, such that it minimizes this one. I will not repeat, like you can verify this. It's just gonna minimize this one. WE over UE, summing over all paths. Yeah. So it's again like, okay, this is just the shortest path problem with the different kind of weight. The weight is now like, for each edge, the weight is WE over UE instead of WE only. So this you can compute fast, right? Just compute Dijkstra, use Dijkstra when the weight is this one. Okay, you can compute it fast in linear time, basically linear time, m plus n log n, but you now need to analyze the width. And if you look at the width, like you're gonna get something similar, like before it's gonna be at most opt times this thing, and you can bound opt by the number of opt of max flow is just at most m times the max capacity. So that some trivial way to bound opt. Okay, so you get this one. So m times something. In unit capacity case, this is just m, but in capacitor case, this is like not really m, not polynomial time. But if the capacity is not too big, then it's still good. Okay. So this is basically the drawback, like the width of the best bang per buck algorithm. Like kind of depends on the maximum weight and capacity. So the running time is not polynomial. There is a nice and quite simple technique called width independent weight update. I wish to teach you this, but we will not have time. So I can give you a pointer, but yeah, like it's really nice actually. But if I have one more class, I can teach you. But yeah, okay. All right, but what we're gonna do is that today we're gonna see the different way to reduce the width. Like the width is gonna be like small, okay? Like what we're gonna do today is like still do something in the same framework where you need to come up with the oracle, and the whole framework still depends on the width of the oracle. But we try to like some clever way to come up with a good oracle that is not just finding best bang per buck variable, and the width is gonna be small. Okay. And the example is again we're gonna look at bipartite matching problem. So let's say that the graph is bipartite. I will exploit that it's bipartite. Actually, sorry. Go back to this one. Just an easy quiz. Suppose that you want to find minimum cut, like to get approximate minimum cut, what you need to do? Like, is there any different from solving Maxwell?
To the dual?
Yeah, like you really just use the same algorithm, right? You have a minimum cut. The LP for minimum cut is covering LP. But so if you want to find approximate minimum cut, you can just look at the dual, which is Maxwell. And we have developed a generic way to get solution for packing LP. And whenever the oracle return infeasible, you get a dual solution, which is min cut. So whenever, basically, if you want to solve covering LP, just look at the dual, which is packing LP, and use this weight update framework. Okay. So this is true for any packing covering. Yeah. Okay. Okay. So we're gonna look at like bipartite matching problem, and I want to note that like when you want to solve bipartite matching, the maximum fractional matching and maximum integral matching are the same. Do you recall why this should be the case? Like the size of, yeah.
You can extend, wait, I don't know if this is right actually, but maybe you can extend, like, if you generalize this graph to like a max flow min cut with a source and a sink, we already learned that. the best fractional solution to that is as good as the best integral matching. And so like if you extend this problem to that, then
Very good, very good. So let me repeat what Rob just said. So when we learn about MacFlow, right, we learn that when the graph has integral capacity, then maximum flow and maximum integral flow have the same value. You can always find like a MacFlow whose flow value is integral. Okay, and that will imply that like fractional matching and integral matching have the same maximum value. Why? Well, like because matching can be solved using MacFlow. Like when you have a matching instance, you can reduce it to MacFlow instance here. You remember this? Like we add a source and sink and put capacity of each edge to the source and sink to be 1. This can be 1 or infinite, and it doesn't matter. But this is like a graph with like a MacFlow instance with integral capacity. And you have seen that like the flow in this G prime just correspond to fractional matching in G. And integral flow in G prime just correspond to integral matching in G. But these two things have the same value, have the same maximum value. So these two things will have the same maximum value too. Right. Okay. So that's just like some reminder about like matching. Okay, but our goal now is to compute 1 plus epsilon maximum fractional matching. So the size is going to be the same. Like it's going to be max. We will return we will return fractional matching, not integral one. Yeah. Okay. That's our goal. Okay. So this is just to remind you some fact, but the goal is still to compute fractional matching that is approximately maximum. Okay, so that is we want to get a solution here that is like basically maximum up to 1 plus epsilon factor. Okay. And previously, yeah, we have seen the bank per buck oracle where like the width is n, the running time is linear, and the algorithm is just like find the edge with minimum weight here. So that's running time is m, width is n. Width is too big. We want better width. Okay. So what we're gonna do here today is just you will find oracle with just 2, and running time actually is m log m. So the running time is a bit worse, but the width is much better. Okay. So before I describe the algorithm for the oracle, let me recall like for each round of the oracle is given the weight for each constraint. So the weight is for each vertex here. And let's say the W is the sum of the weights. The capital W is the sum of the weight. And now I'm just going to define the edge weight in a natural way. The weight of HE is just the sum of the edge endpoint. Sum of the weight of each endpoint. And the weight of subset of edges is just a sum of the weight on the weight of each edge in the subset. Okay. So okay. So actually, let's try to motivate the algorithm a bit. Yeah, like we see that the previous algorithm has like the previous best bang per buck oracle has really high width because it's just try to put all into one variable, right? Put the value really that is really big like opt into just one variable. So we try not to do that. We try to basically find many edges that are like and put value into different edges. That's the so that and hope that maybe now the width is smaller. Okay. And the algorithm is basically this. I'm just gonna sort edges according to its weight. So the best bang per buck edge is just gonna be the first one here in this order, but we just sort all of them right now. And now I'm just gonna find a matching in a greedy way, such that my matching, the total weight on edges of the matching is at most W/2. How do I find this? I'm just gonna say that initially my matching is empty, and then I pick an edge that is the lightest one, the first guy in this ordering, right? And then try to add this edge into the matching. And if the weight is still less than W/2, then I add it. Then I include it. And then I just gonna remove the endpoint UV from the graph. And then repeat. So you have a graph, pick an edge with the minimum weight. And then if the weight is still small, not too big, the total weight is not too big, remove it from the graph, find another edge, and remove, find another edge, and remove. So obviously the set of edges that I add is going to be matching, right? They are disjoint. Okay. And so I just keep finding this set of edges as long as the total weight is not too big. And once the weight is big, or like it's gonna be big enough, then I just return x, where x is just I set value of 2 into every edge in my matching. So you see that what is going on here is I think I have interpretation. So look at this intuition a bit. Okay. So what we used to do is just to pick the first edge in this order and put value of up there. Now we try to get edges, multiple edges with still good bang per buck, because we try to choose the one that has like a small weight, right? The smallest one have the best bang per buck, but we now just choose multiple edges with good enough bang per buck. What do we mean? What does it mean to be good bang per buck? It means that like at least in total, like the total weight is not too big yet. Like the guys on like the guy on the last of this order will have like maybe two big weights. So that's not good bang per buck. So I just try to add many edge as possible that has good enough bang per buck. Okay. So instead of just single edge, we don't do that. Now I also have the constraint that the way that I choose these edges is going to be a matching. Why do I want a matching? Why don't I just let's say I pick like a first few edges in this order without the constraint that the edges that I pick form a matching? Well, because if it's not a matching, right, it could be the case that all of edges that I pick, like when I sort them here, the first edge is here, the second edge is here, the third edge is here. Like all of them, let's say it can be incident. Let's say all of them are incident to one node, V. And then I'm just gonna put the value of 2 on every edge here. So the total total value of edges, like the total xe on this node here, can still be big. We want to bound this thing. We want to bound this to be like something like 2. But if all edges here that I pick are incident to one node, this is gonna be like a big, which is we don't want that. But if the set of edges that I pick form a matching, then you see that like this thing is gonna be at most 2. You see this? Okay. So if we wanna like get the width to be small, we should choose the matching, or at least choose it such that the set of edges have like a small degree, like each node are not incident to many edges that we pick. Okay. Questions? Okay. Okay, so by the way, note that this oracle never returned infeasible. Like it's just gonna return some matching. So actually it doesn't require us to guess opt. It's just gonna return something. And formally it's just gonna like I will show this. I will show that this oracle will return x such that the size of x is going to be at least op integral, which is just the same as op fractional. We know this. And also this is satisfied. So this together implies that this is a feasible solution for the oracle. And we also have this. That is, the width is at most 2. We will prove this. Once we prove these 3 things, then we are done. Okay. And you see that, like, this implies that it's feasible oracle solution. Here the width is 2. So we get this. And the running time of this algorithm is just for sorting, basically. That takes m log m. All right. And so if it means that if we plug this oracle into the algorithm, the LP, the whole framework, we're gonna get a mesh, like a fractional matching of this size, and the running time is gonna be something like width times log n many iteration. In each time you compute the matching and update the weights. And the weight is gonna be, we're gonna update the weight on at most n nodes. So the total running time is something like this. So last time we saw an algorithm that have running time something like mn, and we improve it to n squared, but now it's like linear in m. So it remains to prove these 3 things. Okay. So let's prove it. Okay. So this is easy, right? Like this is just to say that for every node v, what's the total x value on this node? But the total x value on this node is going to be at most 2, because look, if you pick at any nodes, let's say this is our matching m. If v is not incident to m, then this is going to be 0. And if v is incident to m, is the endpoint of m, this is just going to be 2. Because we set the value of xe here to be 2 for every matching edges. Okay, so this is good. How about this one? Let's compute. Well, WAX is what? It's just you write down the constraint on each, write down the constraint for every node, multiply it with W, and sum them up over all nodes, which is this one. And we can rearrange it to sum over all edges, XE, and the sum of two endpoint here, right? This thing is just 2. This thing is the weight of an edge. But so, and we have like we have 2 when we have 2 if E is in M. So we can just sum over all edges in M, the weight of an edge times 2. This is the total weight of the meshing times 2. But the weight of the meshing is at most W over 2 by construction, by our condition. So this is then at most, W times 2 over, times 2 over 2. So W is just, and this is just like a 1, W times 1. So this is good too. Okay. So basically the fact that we have this condition is to control, is to make this, it implies that like WAX is the most W1. We want this. Okay. And the last thing is that we want that the size of x is at least opt integral. Okay. So how to prove this? This is going to be non-trivial actually, but let's prove it still. Let's say that M star is the maximum integral meshing in G. Like, forget the weight and everything. This is M star is just the maximum integral meshing that we don't know, but we gonna look at it for analysis. And to prove this, it's just equivalent to prove that the meshing that the oracle return is as big as M star over 2. Right? Why? Because this thing is sum over edges XE, right? But this is just the this is 2 if E is in M. So this is just 2 times size of M. And this is just by definition the size of M star. So to prove this, it's just the same thing as saying that 2M at least M star. So we're gonna prove this. Okay. Wait. Okay. So to prove this one, or to prove this one, let's analyze something. Okay. Suppose that EI and EI star is like the I lightest edges in M and M star. Okay. Now I'm gonna show that the weight of EI is at most the average weight of these two guys in M star. So I mean like this is M, E2, E3, E4, EM, E star 1, E star 2, so on. Like the weight of this guy is gonna be at most. Actually, I'm gonna prove that the weight of this guy is gonna be at most the weight of both of this guy. Like I can replace this by min actually. And the weight of E2 is going to be at most the weight of this guy and this guy. And so on. Min E1 star. Okay. So let's prove by induction. Well, the best case is that like E1 is the lightest edge. So it's going to be lighter than any edge. So it's lighter than both of these E1 star and E2 star, which means that if lighter than both of these, so it's lighter than the average of this. So we get this one. Okay. So now let's prove like for the inductive step, right? Well, I claim that like if you look at the first two I edges in M star, there's going to be at least two guys in this set, at least two edge in this set that are still disjoint from E1 up to E1 up to EI plus 1, EI minus 1. So now that I want to prove this. So I mean like this, like that maybe I draw it with this color here. There are this is M, like this is like a E1 up to EI minus 1, and this one can be looks like this. But there's going to be at least two edges that are kind of disjoint from all the orange edges. And the reason is just that, like, okay, there are I minus 1 edges here, there are two I edges here. But like, if you look at each of the edge from the orange set, okay, it can intersect to at most two red edges. Because the red edges, oh, I see, you can distinguish the color. Yeah, let's write green. Okay. So each of the orange edge can intersect at most two green edges. Because the green edges form a matching. The green edges is a matching, so any edge can intersect to at most two green edges. There are many green edges, so like I minus 1 edges can overlap with at most two I minus 2 green edges. So there's going to be at least two green edges that are disjoint from the purple from the orange one. Okay. So it means that let's say that this is like two edges, EJ prime. These are the ones that are disjoint from the orange edges here. So it means what? It means that if you're gonna choose the next EI need to be lighter than both of these guys. because we choose EI to be like the lightest one, the lightest edges among all that are still disjoint from the previous orange edges. But these two green edges are among the candidate. So this guy is going to be lighter than both of these. So yeah, let's say that EJ, EJ star and EJ prime star are disjoint from this one. So we have that the weight of EI is at most the minimum of these two. Okay. So it's going to be at most the average of these two. In particular, it's going to be at most the average of the heaviest edges from this set. So this, like, I just picked the last two guys instead. Okay. So I hope we are good now with this. And now, once we have this, when we are basically done, okay. Now I can claim that M is going to be as big as M star up over 2. So why is this? Well, let's see. Like, what you need to do is like, so don't look at this yet. We need to say like, the way that we construct M is that we keep adding edges into M as long as the total weight is not too big. Right? And I want to say that even after I add this many edges into M, the weight is not too big yet. So that would prove that M is as big as this one. Okay. So let's try to analyze the weight after adding this many edges into M. So after adding this many edges into M, the total weight of M is what? It's just going to be the weight of the first M star over 2 edges in M. Like, just sum the weight here, right? But from our proof, we know that the weight of this guy is at most the average of these two guys in M star. But now what's this? This is just to sum like over the weight of everyone in M star now. We sum over like M star over 2, but for each term we take 2 guys from M star. So the sum is just the sum of the weight of M star over 2. And the weight of M star is at most total, like is at most W. Why is that? Why is it the case that the weight of M star, which is the sum of UV in M, UV is going to be at most the sum of the weight of every node?
They're disjoint.
Exactly. This is a matching. M form a matching. So like every node will basically contribute to the sum at most once. Okay. So we get that this is at most M, this thing is at most W over 2. So it means what? It means that even after adding this many edges into M, we are still within what budget? So it will try to add another edges after that. It might stop after that, but it has at least this many edges in M. So we're done. Like we will continue growing M after adding this many edges. And if this is true, then it means that this is true. So we prove everything. Okay. Okay. So what do we get so far? We see that like many times you can try to come up with better oracle. Not just like the best bang per buck oracle is like a standard way to do things, but many times you can like try to not focus on just one edge, but add more guys. Yeah. And you see in the homework that there are like nice application of oracle with small width. You like from here you can see that here we get like a fast algorithm for maximum matching, but in the homework you see how to get distributed algorithm for maximum matching, for approximate matching. Right. Good. And I will ask you to basically come up with different oracle. Like I gave you enough hints, I hope, and like you need to come up with some adjustment. Yeah. Okay. Okay. Any questions? Okay. Yeah.
So is the intuition for why we picked 2 as what we're setting XC to be, is that so that we could do I guess everything we did where we like bounded the size of our set by like at most like twice the size of the optimal set? Because like what would happen if we picked 1 here?
Oh, if we pick 1, then it seems like the width is better, but the size is not as good, right? So when we pick 1, this is gonna be 1, but this is gonna be just at most like this is just gonna be over 2. But we want this to be like basically close, like at least up or at least like this much. Yeah. Right. But the general like idea is really just this. Like you might see that okay, it seems fragile. Like you need to pick 2 exactly, but it's not quite fragile like that. Like the point is like as long as you try to pick many good bang per buck edges, and you should pick a matching so that like they don't concentrate to one node. Like once you have start with this idea, then you can just try to adjust the parameters so that things work out. Yeah, that's at least how I approach it. Okay, good. So yeah, again, I actually put out like 2 questions into the homework. Sorry, I put it so late, but yeah. But I hope you have a look. It will be both problems will be related to the exam. Yeah.
Would you recommend if we haven't started all of the first 3 questions that we try to do the last 2 problems, because I think it's 4 out of 5.
Look at like the last 2 and maybe discard 1.
Okay.
From the first part.
Okay.
Okay, so yeah, that's it for MWU. If you learn about ML, you're gonna see some version of this still. If you learn about game theory, you learn like previous year I taught about game theory aspect of this, but I want to switch to algorithmic aspect more. So so you learned it in this year. If you want to learn about game theory aspect, you can look at maybe like the YouTube video that I have for this course. Okay, so we're gonna see each other on like for the last time, like for the last class on Tuesday to review the exam.